Okay, so this is a recap of the organic chemistry mechanism, and this is a week 13, and you have another week. This week we do not have the online quiz, so we just have to focus on starting this problem set. So first one is an electrophilic addition, and then this one I kind of give you a brief overview on that. So I will just try to solve it and then give you the overall overview based on these problems. Okay, so let me just simply try to solve the problem. So complete the mechanism for the following reaction by drawing the proper arrows. So organic chemistry, the arrow means a flow of an electron. So when you draw the arrow like this, that means you have a 2 electron moving in. Okay, so those are the intentions. So it could be this, or when you see the bond, right? That can move as well because bond has a 2 electrons as well, right? Sometimes if you actually go and attend the class in the organic chemistry in the organic chemistry class, not the general chem 2. This one is actually dissociated into 2 parts, and this is called a fish hook, and there's each fish hook is a 1 electron. But I'm pretty sure we are talking about the arrows. This one is quite conventional, so please try to remember. So having said that, what I'm going to draw here is, okay, this one, H plus and Cl minus, they are dissociated into. This electron in the pi bond will try to form and make a bond. And then they have to decide which way they form this hydrogen bonding, and then they will form the hydrogen bonding here and develop the carbocation on the top versus if you do that, okay, so this is a methyl, and the hydrogen can form the bonding here and the remaining hydrogen, and then this will be the carbocation. So they have these 2 scenarios, and then what you can find out is, okay, this is a carbon with the neighboring bonds are all carbons. So this is a tertiary carbon, carbocation. And whereas this one, you have a carbon here, and you have a carbon on the other side. And there's only 2, so this is a secondary carbocation, right? And which one is more stable? The tertiary carbocation, so this is not going to be favored. Okay, so once you have formed this complex, and then now this chlorine, I just highlight these 4 lone pairs, not only satisfying the octet rule, but also this one is trying to act as a nucleophile, looking for something that is positive, right? So they're looking for something positive. They can go here, right? And they can make a bond. And so therefore they make this bond here. Now the new bond of chlorine is happen to this side, right? So the story that is actually simplified. Okay, there is a double bond, and this chlorine should form after being protonated. It looks like a chlorine has formed to the one that onto the methyl side, and essentially what you really need to think it is the really action happens by this hydrogen likes to form the protonated double bond, and they develop the cation, positive charge, other side of the carbons, and then they are ready to accept the bonding so that they can satisfy the octet rule, and they can get rid of the carbocation charges to be neutral carbons and so on. Okay, so that's the exercise, and you can go and recheck at the YouTube on the Google Drive. Google Drive has the links for this. Okay, so I want to go back and then do the recap. So one recap is what I can say is, stability of carbocation. Okay, primary, secondary, tertiary. Okay. So one way to look at it is I like the tertiary to be you can think about this way: carbon, carbon, carbon. Okay, and that's the one that usually the reason is because if you have a CH3 bonding, this is the one electron donating group. Okay, EDG sometimes. So this is an electron donating group. So that's why it's called the induction effect. So they will donating it. They'll be donating it. The threes are trying to donate the electron. They can neutralize. So they are the one essentially the most happy state. Okay. Compared to the others. So this one is a secondary, means you have a carbon, carbon, and hydrogen. I always try to keep in mind that this one is more like a little arrow trying to donate the electrons, and that will be a good practice for you. And primary means essentially you have only one, and then H. Okay, so that's a case that where you're seeing this. Essentially this is a one that when this is attached as a part of and then you lose a bond and develop this carbocation, and that's the one that's more stable, and then the secondary is the next to it. And the second one that I like to go is go to the deeper and then trying to give you a different perspective, is essentially carbocation. What kind of a hybrid orbitals? What is the geometry? This is important, and I kind of explained that in before. And in this problem that you see, which is they develop the carbocations, and when there's a methyl is attached to here, and they develop the carbocations here, and this carbocation, this one, okay, and is an sp2 carbon, and their geometry is triangle planar. In a fancier term is trigonal planar structures, but I'll just call it triangle, and carbon sits in the middle. Okay, so that's the structures. So if you see this one, the geometry that you have to develop, the concept is, let's say, okay, let me just put a piece of paper. So three-dimensionally, this is a piece of paper. Your carbon is sitting in here, and the methyl on the same plane, carbon is on the same plane, and then they form these cation charges, and then these are forming this triangle. And I'm just going to simplify this. This is a carbon, but just make a dotted line here. Okay, so trying to really emphasize the triangle nature that's this one have on this plane, right? So they form this triangle plane, and is ready to accept the lone pair electrons and coming from the chlorine. So let me see if I can put the chlorine here, which is the lone pairs. And this chlorine have an option whether this lone pair can form the bonding from the top, right? Or they can form the bonding from the bottom. Okay, so this is a geometrical concept that you can develop. This is a little higher end, but I'm sure that some of the difficult questions require this understanding. So, but once you finish that, and then I can use a space on the right to explain it to you that, okay, so carbon, and I will keep this one as it is, right? So this is a one, but this is, if you're going from the top, and then that will form the bonding chlorine, and then this one it will be a methyl, right? And if you're going make a chlorine, make a bonding from the bottom, so my habit is make a bond, first this will define the plane, right? By writing this you can define the plane, and then the chlorine comes from the bottom. Oh. So I'll just to be consistent, chlorine comes to the bottom and the methyl is going to the top. Okay, so this is the same thing as the one that you see here when they see the stereochemistry natures, and either methyl chlorine, right, or actually chlorine can be from the top and methyl can be at the bottom from the structure that you see here, right? So that will be the case, but now let me talk to you once more. This second portion is related to the third one, which is chiral carbon center, C star. This is the one that we have covered when we actually even the chemistry 1 class, and there are some students that just taking the chemistry 1 and in our school, so we still want them to develop their insight to look at the stereochemistry, whether the compounds is a chiral or not, and then this is a chiral carbon center, and chiral's carbon center, if you remember, and that means the requirement for this is an sp3 carbon, but that means tetrahedral structures and 4 different attachment. In the last week, I talked about even the optical isomers or mirror image isomers for some compound that is an octahedral base, and this tetrahedral base is actually much more well known and very, in a way, well studied and well understood. And there's 4 different attachments. Okay, so in a way that if you I'm going to draw those tetrahedral structures. Okay, so like this. So this is not on the plane. Those the lines are on the plane, and you should have alpha, beta, gamma, delta, and then okay, this is a chiral carbon. It can have an isomers, right? So if I looking at the question here, and if I can make a copy, make a paste. So I just paste an images, the same one as the top here. But here I am going to essentially make this, really make it as a complete case. So this was a, okay, so this is not 5. Okay, this is a 6, has to be 6. So this ring was something looks like this. Okay. So that was the same compound as the one that's showing at the top. It's essentially a cyclohexane ring, and then you have this attachment. And so I will do the same thing. This is a cyclohexane ring, but this time what I'm going to do is, this is a cyclohexane ring, right? Cyclohexane ring. But now I'm just wondering, what about if I put a methyl group here? The one at the top, your original problem has no methyl. It's just a simple cyclohexane. the carbons. So I am just going to highlight it one more time to talking to you on this. So the main difference in the one in the top, this is not chiral center, not C star. But this one, this is a C star. This is a C star carbon. So this is too thick. This is a C star carbon. Do you see that's because if you look at the carbon here and carbon here, and this is a tetrahedral, and this, the way that you count this attachment, the one that you count this attachment, they are not the same. So it's the alpha and the beta attachment onto the tetrahedral carbon. This is a case where they are not the same, right? So therefore, this is a chiral center. So that's why you will have a racemic mixtures. But in our problem, this is not a chiral center because the way that you're walking in, the way you walk in and count the attachment, they are the same. So it's not going to differentiate. So that's why you don't need to show that there are differences. Just as it is good. Okay. So that's really the in-depth discussion of the first problems. The second problem that I am going to say is what is called the carbo-cation rearrangement. And so this is a one that I am going to give a little explanation before. So if you compare to the previous problem, this is a H plus. So okay, there's a hydrogen, and I see the double bond, right? So then you can decide, well, which way this CH bond would occur. So first thing is protonation. Oh, this is too thick. First thing is protonation. And you can think about the protonation. So once they protonate, you can think about, well, they can develop the positive charges here, and then they can form the bonding. Okay, so they can form the bonding here, and then pretty much those double bonds are gone, right? So I can see the carbon, 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 and so that's the way it is. And then if you just follow the same logic before, this is a secondary carbon, and that's a primary carbon, so this is the one that they prefer, and then the chlorine will form the bonding, then you will expect. So therefore, you will expect something like this, carbon, carbon, carbon. That's the one that you will expect because that's the one previously positive charges was developed, and then the chlorine minus will form the bonding. But what you see is this is not the product that you will see. You are seeing the different product where the chlorine is not attached to here, right? Chlorine is actually attached to the other bond, carbons in your neighbors. So there's something more that more complex reaction should occur. And this is this point of this idea that once they develop the carbocation, they can essentially they are free to move either in this case methyl shift, and sometimes they call the methyl shift. So when I took my organic chemistry before, it actually methyl shift is a little less common. There is a hydride shift. And they are cousin to each other. Okay, if the hydride shift is not available, then they will do the methyl shift. Okay, so this is comes in those kind of priority. So hydride shift means the whole hydrogen with a bonding, or methyl with a whole. This one is trying to move to somewhere. Okay, they form the new bonding and try to. And then the whole thing is why this is happening this way, because of they want to what do you call? They want to increase the stability of carbocations by doing this shifting method. Okay, so let me delete that, and then I'll solve the problems to you right here. Okay, so this is once again. This time I'm going to solve the. I'm going to start with a recap. Okay, do you remember this time the tertiary carbon, secondary carbon, primary carbon for carbocation stability? That's a stability, right? Due to the electron donating nature of the CCl3 bonding. So what you can see here now is, okay, I know that's the one that's stable, and carbon with an hydrogen, that's hydrogen. Right? This is the same logic that I've been talking to you, but some cases, and I am going to delete this. Okay, so this is obvious. So now just let me focusing on this problem. Some cases when you have a secondary carbon, and on top of that, when you have this carbon has ability to shift something. Okay, if this one is a CH3, this is a very similar to our problem now. Okay, so if you look at this problem here, you have this carbon, and then they develop the positive charges here, and upon the dilute HCl, so this double bond will form the bonding with an hydrogen, and they develop the positive charges just like you shown up here. And then you can see that this trimethyl attachment onto the CCl bonding is actually cause some unique situation because of their ability to shift the methyl ions, or methide ions. So what I'm saying here is this bonding here, right, can be actually move on to form the bonding with a carbocation there. And by doing so, what's going to happen is, let me try to see if I can copy those. So I just paste the images, right? And then what's going to happen is, because of that, and let me just delete the portion that, and then, okay. So I'm keeping things pretty much the same, but what's going to happen is because of the methyl shift, this hydrogen goes there, and then the new bonding was formed here with a CH3 from your neighbors. I'm trying to keep the color coordination as they are. By doing so, this is gone, right? This became neutral, and then you are developing positive charges here. Okay, so this one looks a little bit funny, so I want to put this one probably to the top, just to. It's the same thing. This is now the tetrahedral. So this is what is called a methyl shift, and it's called a 1,2 methyl shift. Okay, because it is like the from the 1 to the neighboring carbons, they are shifting the methyl. By doing so, you are seeing some changes. Can you now see this one? What used to be the carbon, hydrogen, this is a secondary carbon. But now by doing the methyl shift, you see you are shifting the problem in a different way. What used to be the secondary carbocation now became tertiary carbocation, and this is an unhappy scenario, right? So therefore, they like to do this, and they prefer to do that. And once you develop this tertiary carbon on the other location, and then they will say, okay, the chlorine is waiting for the carbocation to rearrange and find their most stable form. And then they can go and then form the bonding, right? So once they form the bonding, you really focusing on the location of the bonding, and so then you will see that, okay, carbon, 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 methyl, methyl, with a chlorine on the other side, right? So then this is and then you can see that there is a new bonding here, which is a carbon here, methyl. Okay, so what used to be this trimethyl now shift to the other side and trying to develop tertiary carbons, and that tertiary carbon, so now you have a new bonding onto this carbon positions, and that's the essentially same carbon structures that is shown up on this side. Okay, are you with me? If do you have any questions, let me know. Okay, but that's the two problems that I'd like to talk to you about this. So this is the slide that coming from your class, and then this is talking about carbo-cation arrangement, and then how this one can be the case. And this is the one actually show the hydride shift. You can see this. This is on hydride shift. What you can see here now is, okay, when the bromine is left, right? So when the bromine is left, this one becomes carbocations, and this carbocation is secondary, right? You can see that that's a secondary carbons. And so once the essentially Br minus has a left and the leaving group, and then now you can see that there's an option that this methyl group shift, or this hydrogen, right? So this is on hydrogen, your neighboring one, and this one, if I move this one, just like a methyl shift to the other side, you'll be the same secondary carbon. So nature would not want to do that. But if you look at the hydride, which is much swift small ions, that can essentially, why don't I neutralize by this hydride shift and making a bond to you, right? So this is too much information, so I'm going to just delete that. That is what is really key here. So by doing so, you became and the new bonding, right? So this one becomes, by shifting this, you are developing positive charges here. What used to be the positive charges here is now gone, and then you'll form the new hydrogen, and then the positive charges here, right? This is a 1,2 hydride shift, because you are essentially, this is the one that has been shifted from neighboring carbons. So once you develop these positive charges here, now this is a nucleophile that can form the bonding, and so they can form the bonding here. So this is a rearranged one, right? So this is what I'm trying to say, and now I understand why Dr. Ma has this complicated notation. When it's not rearranged, you can just simply develop the charges, and this one can just form the bonding here. But this hydride can move, and then they develop the carbon here, which is a tertiary carbon, and that's a better stability. And that's the one that is now can form the bonding with the nucleophile. Lone pairs in the oxygen, so they can do that. And this is a mixed product, but this is will be the major product that will be the one. So sometimes this hydride, right? So this whole bonding, so you do have negative charges, and the methyl with the bonding. So this is actually negative charges, so that they can the whole unit can move around to neutralize the carbocation next to it, and that's the one that what's going to happen. And this is the same thing that I also find that is useful. Once you lose this bromine to bromine minus, you develop the charges here. And this one is carbon. There's only one carbon. This is a primary carbon, right? And this case is okay. So then why don't I have this methyl trying to form the bonding as a methyl shift. In a strict sense, it's called a methyl shift because the anion form is one. They for hydride shift, so it should be a methyl shift. Otherwise, methyl shift and hydrogen shift is the name. But somehow the organic chemistry area, they just call it hydride shift, and then they say methyl shift, which is not consistent, but that's the way the community use it in most cases. So by doing the methyl shift, which is strictly speaking, they are shifting this, you develop this newer types of carbocation, which is a tertiary, right? From the primary carbocation, from the tertiary carbocation, this will be the one. And then they'll be ready to form the bonding on here. So therefore, it will be a carbon with methyl, carbon with a bromine on there. And then you keep the carbon here. So this is my habit that trying to make sure that what kind of the carbon skeletons and which carbon is attaching forming a new bonding. And that's a good habit for you to have, because in the beginning you have a carbon here. It's almost like a clover leaves, right? It almost looks like a clover leaves, and now it looks like 4 carbon with a methyl sticking out instead of having carbon with a 4 sort of the carbon bonding. So this is always you essentially having the shifting, the hydride and the methyl, and trying to form the new bonding. Okay, so I will stop here, and then actually there are new portions, and then I will going to talk about SN2 and E2. There's some extra questions that I'm trying to review, but this is pretty much I kind of covered that, and then the next session that I will probably focusing on the other one. I really want to go back to emphasize the important nature. If you understand the C plus carbocation, there's only 3 coordinations here, right? The 3 coordination has a trigonal planar structures. So it's like on a flat piece of plane, those 3 carbons neighboring the carbocations are on the same plane. And because of that, sometimes this geometry problem can be interesting. Okay, so this is something that I want you to keep that in mind, and to do a practice for you. And then this a little bit in-depth problem. Once you have this carbocation and they're forming a bonding, because of this nature, sometimes they can discriminate the bonding from the top, bonding from the bottom, make the differences. These 2 compounds are different when you have the rings around it has asymmetric methyl attached to it, and then because counting the bonding from downside and counting the bonding from the top side is not the same. So these are the different, and then if you ever have a reaction like this, we call it as there's a racemic mixture, because an equal opportunity to form top and the bottom at the same time. Whereas this carbon is not chiral, because the way that we count this bonding from this side, from the bottom side is the same. So this carbon is not chiral. So essentially, it doesn't matter whether the bonding is happening from the top or bottom. I don't need to distinguish. So that's why I put an X sign here, and then you'll see this. We can just put it in the one as it is, right? Okay, so I will